Okay, so thank you for this opportunity to discuss what I call extreme precision stellar spectroscopy.
Oh, Dainis, I asked Katja to kindly introduce you before.
So I apologize. Sorry.
Please, Katja.
I misunderstood.
Okay, so our speaker today is Dainis Dravins. Dainis did his undergraduate at the University of Lund and Uppsala in Sweden. And then he was a postdoctoral fellow at Caltech in the US. And since 1984, he has been a professor of astronomy at Lund University. And he has also worked periodically at several other institutions, such as ISO, both in Germany and Chile. And today, Dainis' talk will be on extreme precision stellar spectroscopy. Okay, Dainis, you can start. Thank you.
Okay, thank you. So already Fraunhofer 200 years ago had quite some precision in his work, but today the frontiers are more or less defined by the let's see if this is by the extreme precision radial-velocity spectrometers. And these devices have now been developed and set up at several telescopes, several large telescopes all around the world. And they enable not only the search for exoplanets through the radial velocity method, they also enable stellar spectroscopy with unprecedented precision. And I will try to highlight some ideas in that direction. A question one can ask, what information is hidden in the highest resolution and in the spectral details? Well, what we're studying, of course, are stellar surfaces, because stellar surfaces, that's for where the light comes from the sun, from the stars, most of the light from the galaxies and so on. That is where radiation detaches from matter. And one can argue that that is our primary interface to the rest of the universe. I mean, most that we know of the universe has been through light coming from stellar surfaces. Now, we can study the solar surface, of course, in quite some detail. For example, we've seen the quite recent images from the Dainis Solar Telescope on Haleakala, and not least, maybe seeing the tiny structures in between granules where we see presumably the footpoints of magnetic flux concentrations. We can look at solar granulation away from the solar disk, center of the disk, and then we see the beginning, or at least something of a three-dimensional structure of the solar surface. And these things have been possible to model over the last 20 or more years. There's been a generation or several, say, takes of three-dimensional hydrodynamic models. Here are images, synthetic images from two of these. To the left for a hotter star, 6,500 Kelvin, to the right of a cooler star, 4,000 Kelvin, and they are here seen on the same spatial scale. So one sees a difference in the size of granules and also in the vigor of granulation. So these things have been with us for quite some time now. But what is new is that one starts to get realistic to use these models for synthetic spectral calculations, not only of idealized spectral lines, but complete spectra, basically taking all the lines, laboratory data from databases such as VOLD or others, and to compute synthetic spectra at hyper-high resolution. This expression hyper-high meaning step sizes in the wavelength domain that corresponds to a resolving power in excess of maybe 1 million or so. You cannot use the word ultra high because ultra high is already taken by 200,000 type of resolutions. And such calculations have been made by the collaboration, including people like Carlos Allende Prieto here at the meeting. And these are some examples. I mean, to the left is a cooler model where, of course, one recognizes the black body curve. There's the negative hydrogen ion bump at 1.6 microns. There are a lot of molecular lines in the infrared. Or we have a hotter star where, of course, you see the Balmer line progression, a Balmer jump, and so on. So these models have like 3 million spectral data points throughout, I mean, from ultraviolet to the infrared. And what they show, of course, are some things which are known previously. We have the line asymmetries, wavelength shifts. And to remind ourselves where they come from, here were such calculations for a single idealized line from a 3D model where is shown for 5 different line strengths, and each of the thin lines here is that for one particular time step or one snapshot, a temporal snapshot in the model. So you have the simulation area, volume. At each snapshot, you take the average over a space, you get one line profile, you get a sequence of these, and then these end up in this dark curves, which are then showing especially for the weakest line, a convective blue shift because the lines are averaging out with a statistical dominance for the rising elements and so on. Now, this is for an idealized single line. So here the line shifts are sort of coming directly from the calculations. But if we go to a complete spectrum, things are not that simple. In a complete spectrum, lines may get asymmetric and skew, not only because of convective phenomena, but also simply because lines are blended with something else inside or next to the line. And in such situation, here an example for an iron 2 line somewhere in the red, for a cooler model and for a hotter model. In this case, it is checked against one-dimensional models. I mean, where there is no convection-induced line asymmetries, that the lines indeed are symmetric. The bisector here is a straight line. And in such a case, you can conclude that this line asymmetry, this bisector for these lines, where the scale is 10 times expanded up at top, comes from the atmospheric dynamics. And these shifts, they depend on a number of phenomena on the line properties. Some of these properties are maybe easier to intuitively understand. One such thing is that lines get different convective blue shifts depending on the wavelength region. I mean, if we take a certain temperature disturbance and we look at what is the black body radiation contrast between the dark and between the hotter and cooler elements, that contrast is much greater at short wavelengths than it is in the red and infrared, simply because of the shape of the black body curve. And also then the statistical bias, the dominance of the blue shifted granule components gets more pronounced in the shorter wavelengths, as seen here for pairs of lines of roughly similar strength in different stars of different temperature, where the blue bisector and the blue profile is for a line at the shorter wavelength regions, 4, 6, or 7 nanometers, and the red ones are somewhere in the redder ones. So this is sort of understandable pattern. What has been studied extensively in the past is something that is maybe less intuitively obvious, perhaps, and that is the change of bisector shape and wavelength shift as function of spectral line depths. Here, for a model that is close to the solar one, we have the bisector for the strongest lines. This is up here, and again we have a tenfold expanded scale at top, and there is a progression such that weaker lines get successively more blue shifted, and they follow basically the letter C. If we now take this, what we just had, this was for the near solar model, and we compare this for hotter stars, we find that the progression of bisectors gets more pronounced because the convection is more vigorous. We can extend this to cooler stars. We go here to 4000 Kelvin, something like K8 main sequence star, and we find that for typical iron 1 lines, the bisectors are now almost, not quite, almost straight, because we don't have much of a convective dynamics here. We can repeat this for RN2 lines, and there is not very significant, but there is a difference in how they perceive the atmospheric dynamics. I mean, the RN2 profiles, bisector patterns are somewhat different, and all this, of course, then changes from cool stars over solar type temperatures to the hotter ones. Now, you can ask, do you believe these models? Should you believe the models? And how do we test them? Well, one possibility is to do spatially resolved stellar spectroscopy. That is to do spectroscopy across spatially resolved stellar surfaces. And to see what can be tested and what is predicted, let's just check again what these simulated synthetic spectra provide. We get the line profiles and spectra for different positions on the stellar disk. In this case, for the Cobalt consortium computations, there are 21 positions on the stellar disk. There is something at the stellar disk center, mu cosine theta, that is the angle to the normal, equals 1. Some gradually further away from disk center and upward close to the limb, where of course we have a significant limb darkening. And so there is like 20 or so different center to limb positions and azimuth angles. Also, we can look in detail. I mean, what is this difference in azimuth angle? And this is now at the same center to limb position distance, but different azimuth angles. And all this we have for then maybe 20 or so time steps. And that means that if we take a model for a single star, its spectrum of a resolving power of 1 million or more has then maybe 3 million spectral data points. That is for each of some 20 spatial locations of the star, and for each of maybe some 20 snapshots, temporal samples. And that means for a single star, there are no more than 1 billion spectral data points, which means that even a thing like single star spectroscopy is now going into the realm of big data. But let us reduce this to some simpler parameters. One important feature of three-dimensional models is that the horizontal velocities on the star are greater than the vertical ones. And this comes from mass conservation, basically. We have gases in the granules that are rising. They must stop and turn over before the star ends, so to speak, within a few pressure scale heights. And that forces the horizontal velocities to be significantly greater. One observational effect of this is that the line broadening, spectral line broadening, gets larger, gets greater close to the limb of the star, because there we can see the velocities along the line of sight. The horizontal velocities along the line of sight are greater. And so we have, if we go from the center of the disk here for a hotter star, gradually toward the limb, lines become significantly broader. And the same thing for the sun, not so pronounced for the cooler stars. So to study the center to limb line profiles for stars, we can use exoplanets. People are studying exoplanets mostly for the purpose of studying the exoplanets. But what is somebody's noise is somebody else's signal. So what happens during the transit? Well, the transit is that the planet is transiting the star. If we take the differential signal, the difference between the spectrum and the brightness of the star in different positions, we get in principle the subtraction, which is a sequence of stellar surface patches that at each time has been hidden behind the planet. We only use a planet as a dark shadow, as a dark mask. Now, the steps to retrieve the stellar spectra are these then. The exoplanets successively hide segments of the stellar disk. We take differential spectroscopy to see how the spectrum changes during this moment, in order to find the spectrum of those small stellar surface segments that happen to be hidden behind the planet. And we can compare this with 3D hydrodynamics, from which we get predictions of the center to limb variations of line shapes, asymmetries, and wavelength shifts. And of course, if it would happen that the planet would cover a star spot, we would in principle, given sufficient signal to noise, also retrieve the full high resolution spectrum of that star spot. Now, why does it work? Well, it works because suitable exoplanets are roughly the size of Jupiter. And Jupiter is the correct size. There is in Swedish a difficult to translate word called lagom. And lagom means something that is not too large, not too small, not too big, not too small. A Jupiter is roughly 1% of the area of a solar-type star. The sun has like 1 million granules on its surface. So a 1% Jupiter covers like 10,000 solar-type granules. Covering 1% means it is small enough to give a reasonably good spatial resolution across the star, but is also big enough to average out maybe 10,000 or so granules in order to have a line profile from what is behind it to be reasonably averaged out and not to be overly fluctuating because of the small number statistics of granules. And actually, this image is to scale. It's our Jupiter, oblateness and all, against the solar surface at that particular scale. Well, the principle may sound simple, but the practice requires extremely high signal-to-noise ratio for the spectra. Because if you want to recover a spectrum with signal-to-noise ratio of 100 to 1, perhaps, from only 1% of the stellar signal, that implies that we must have an original stellar signal-to-noise of maybe 10,000 to 1, and that may sound forbidding or prohibitive. These are examples of synthetic reconstructions of such a planet. To the left, a very high resolution of 600,000. To the right, a more realistic 150,000. And so the dots are the original line profiles, and the solid line is what happens if you can reconstruct it with an unrealistically high signal-to-noise ratio of 100,000, and the somewhat wiggly, noisy lines are for a signal-to-noise of 10,000. So for signal-to-noise of 10,000, you can see you get a reasonable reconstruction. Maybe you don't need 10,000, maybe 5,000 or so could be enough. And how do we get this? Well, in cooler stars, we have the advantage that the cool stars have very many spectral lines present, and there are many that are reasonably similar. For example, an iron 1 line of a certain strength at 520 nanometers will carry more or less the same information that another iron 1 line at 525 nanometers or at 530 nanometers. So if we select lines that are reasonably similar, here in one case, in this also well-studied star, HD 189733, these are then, I forget the exact number, but maybe 100 or so iron 1 lines of a strength that are surrounding this average. The average is here, the dashed curve. And there is another, say, averaging here for weaker lines. And these then form what you could call observationally synthesized representative line profiles. They are not one specific line, but they are typical for lines of that strength of that species. And this is something we can then handle in studying things. So we ask, what do we expect? This is synthetic. Here we assume a rotating star. Here is the planet coming in, and this is then the resulting line profile, and you don't see any difference here. But if you divide the instantaneous line profile with that of the profile outside transit, you get the ratios at the bottom. So you get something that changes during the transit. When the planet is at the center of the disk, you get something that looks like an emission profile. Of course, it's not emission. It's something you may recognize from Doppler imaging of star spots. That is also when you have a spot on the center of the star, you get some sort of such a feature. The amplitude here, this is 5 parts in 1,000. We expect an amplitude of a few parts in 1,000. And these are actual observations. This is with the UV spectrometer crossing another well-observed star. And what is plotted here, if you can see it, are actually 14 superposed curves. You may not see much of their difference, but there are 14 curves here during half a transit, a transit from stellar disk center to the limb across this HG 208458. And this is, if we then look at the sequence, we now have this ratio of line profiles. The line profile of these average lines, in this case, it's 26 iron 1 lines, divided by the line outside transit. And so this shows the line, shows the noise level. Again, this is 5 parts in 1,000. So the amplitude here is a few parts in 1,000. And it is from such sequences of data that one can reconstruct what are the stellar line profiles behind the planet. And in this case, just taking out 2 instances during this transit, we have the star, and this is to scale. This is the planet to scale in one occasion. This is the second occasion, one closer to the disk center, one closer to the limb. Here we have the gray dash curve is the line profile outside transit. The blue curve is at the closer to the center of the limb, to the center of the disk. And you see that the line is narrower and deeper, which is natural because it is not rotationally broadened. You can see that the line profile closer to the limb, this one, the brown dashed one, is significantly broader, and that is what is predicted from 3D hydrodynamics. We expect broader line profiles because of enhanced horizontal velocity flows. And you can see that there is a displacement in wavelength, maybe 3 kilometers a second or so between these instances. And that is, of course, the Doppler shift because of the, say, component of stellar rotation at the particular latitude of transit. And this also shows in this case that the planet is rotating, is moving on an orbit in a prograde orbit. So that was the, say, overall changes of line profiles, but there are more subtle changes. For example, line asymmetries and wavelength shifts changed between center of the stellar disk and the limb. Here, synthetic lines for 3 different stellar models, hotter corresponding to F3 spectral type to all the way to the solar type. So the red one is the hottest star, where going from stellar disk center to the limb, we get, yes, an increased convective blue shift, not a decrease, an increase. For the solar temperature, we get a decrease or even an overshoot of the convective line shift. Understanding the central link changes in spectral line profiles is important not only to verify the 3D hydrodynamics, it's also significant for exoplanet studies, because one way to determine the chemical composition of an exoplanetary atmosphere is, of course, to look at what starlight is seeping through the exoplanetary atmosphere. But the light that is seeping through is not the light from the stellar disk as a whole. It is a light from that particular part of the star that is just behind the planet. So that is needed also for in a sort of more precise, say, exoplanetary studies. But anyway, these are the changes centered to limb. So how can we identify those in stellar spectra? Okay, let's recall the Rossiter-McLaughlin effect. It was not invented or found by these people, but they made it popular. So as you surely know, you have a rotating star. One hemisphere is rotating towards us, so there is blue shifted, the other one is receding and red shifted. Planet is crossing, and the remaining starlight then becomes first somewhat red shifted because we take away some of the blue shifted photons, and then the reverse, the other side of the transit. Okay, but it is not only the change of line wavelength because of stellar rotation that matters. The line is changing in other parameters, even in the absence of stellar rotation. For example, recall that we saw that in the spatial resolved spectra, closer to the stellar disk center, the line is deeper and narrower than elsewhere. That means that if the planet is covering over that central portion of the star, it takes away light from the narrower and deeper line, and the remaining light becomes then not as deep, not as narrow. It gets well, shallower and broader. And so the absorption line depth changes when things cross. This is not planet position. So the planet position at the center of the disk, there's a slight, very slight, but finite change in line depth. And there is, of course, a change in the wavelength, because which is not as trivial, because for many models at least, the maximum convective blue shift is not exactly at the center of the disk, is somewhere between the disk center and the limb. So how can this be studied? Well, let's see what we expect for the well-studied star HD 29458, and we take it at a resolution that corresponds to existing spectrometers. To the left is what one expects for a medium strong line, a line of that strength, what typically contributes to the radial-velocity data in extreme precision exoplanetary spectrometers. To the right, for a weaker line, just shows these sometimes are different. The dotted curve is what happens if we have a transition. If we have crossing the stellar equator. The red curve is what happens if the crossing is at some impact parameter actually corresponding to this particular star, because the transit is not across the equator. We then expect a modulation. It's only maybe a meter a second, 2 meters a second in amplitude, but a modest variation of this type with maxima somewhere halfway between the stellar disk center and the limb. The so far probably most precise measurements of this particular star are those made by Nuno Santos and his group with Espresso. And this is from what they found. This is their Rossiter-McLaughlin curve, which is fitted to observations, but there is a small deviation from the fitting, and the residuals are seen at the bottom. And there is something suggestive of something going up, going down, going up again, with an amplitude of a meter a second or so. And if we superpose what is predicted from, it's not a model fit though, it's not exactly the same stellar temperature, it's not exactly the same way of computing the radial velocity, but it's reasonably close. So this is basically what one expects. One expects actually a signature because of the center to limb change of stellar convective blue shift of this nature. I'm not arguing whether this is the best or not the model fit, but the main point here is that these phenomena are now becoming or have become observable with the highest resolution spectrometers. So this is now opening up. It's not only the Rossiter-McLaughlin effect, one can go one step further. But we're looking for even smaller signals. That's not the end of it. A big challenge is to find an Earth-like planet in an Earth-like orbit around a solar-type star. The precision available in the highest resolution exoplanet spectrometers is now approaching the precision that is needed. The Earth is influencing the sun just ±9 centimeters a second. Here is from a simulation whether one could have a slightly lower mass star, 0.8 solar masses, as Earth planet, a period that is out of sync with the Earth's period. It gives 11 meters per second, how things would look over the years. And the conclusion is it should be possible to identify it. But can you? Well, today we cannot. And the problem is not that the precision in the spectrometers would not be adequate. The problem is the stellar variability is much greater than planetary perturbation. The stars are not stable. For this, it would be nice to have stars such as the laser combs, but the stars are simply not stable. So we are facing the stellar spectrum microvariability. So how is the sun changing? This has been studied here is by a work by Nadège Meunier, reconstructing the solar apparent radial velocity changes over a solar cycle. This is then some meters per second, and there is a general change which can be identified as coming from the modulated granulation that is modulated by magnetic fields which are disturbing the granulation, which are prohibiting granules to develop equally large amplitudes as they otherwise do. So that is the main driver of solar radial velocity variations over the solar cycle. These things are now becoming possible to quantitatively study, thanks to a number of the Sun as a Star spectrometers, such as this one at the Harps North at the Telescopio Nazionale Galileo on La Palma, and which has been running now for several years, and where a recent data release from 3 years came from Xavier Demusk and others, and that is publicly available from 2016 and onward. The radial velocity flickering, jittering of the Sun as a star has an amplitude of maybe 1-2 meters per second. Here in a scale from 20 for the last several years, even up to the COVID lockdown situation. And that is an amplitude that is sort of expected, just as a naive guess. The Sun is covered by 1 million granules. Each granule is maybe 2 km/s amplitude. If you average them, you assume they are at random, which they probably are not, but then you divide that by the square root of 1 million and you get 2 meters a second. I mean, this gives you an order of magnitude signal, which of course is much greater than the maybe 10 centimeters a second one would like to measure. So what can we understand? What can we try to learn? Well, we can go back to the models, and we take here, in this case, idealized line profiles, and we look at the different time steps in the simulation sequence. To the left is a cool 4000 Kelvin star, something at stellar disk center. Again, these are some 20 snapshots. There is not much difference between them. The K star is very calm, very quiet. The solar model is more dynamic, and when we add in additional data from various solar disk quadrants, we get more data. So things are changing. But what is it that is changing? Is it the radial velocity of the model? Yes, of course. I mean, sometimes in the model, there is a greater number of bright granules rising, so there are more blue-shifted photons, there is a more convective blue shift. And when there are more bright granules, the whole area becomes brighter. So here is brighter. This is then brighter, the irradiance from the model. This is the apparent radial velocity in this solar type model. So when things are brighter, velocities tend to be bluer, which of course is at disk center to the left and some other position to the right, which is nothing surprising. But what is important to note that it is not only the radial velocity that is changing. Other things are changing in unison. Other things are changing in concert. Here, the line depth also changes. And when things are brighter, lines get stronger. And that seems to be connected to the situation when there is big, large granules, then the vertical gradients are greater in the photosphere, lines get stronger. And line depth is something that can be measured independently from radial velocity. And if there can be a sufficient calibration with line depth and other line parameters, one could hope to use those as a proxy to somehow compensate or correct radial velocity to its, say, true motion. But this is different for different spectral features. We again take from the Cobalt collaboration a synthetic spectrum. This is now for something very similar to the solar case. We zoom in at some limited spectral regions. We recognize, of course, the strongest lines, H alpha, H beta, calcium, H and K. We keep zooming in, and we identify a group of many lines together, a clustering of lines. This is the G band. The G band at 430 nanometers. And the G band is a molecular bandhead where there are many lines from the CH molecule, but also many atomic lines, and the result is a high line density. And that also makes it sensitive to various changes in the physical parameters. So from the model, this is then what we, for the sake of discussion, define as the full G-band. And we also say this is the central part. This is the most pronounced absorption at its center. And then we can ask, how does this change during the evolution of a simulation? We have here in the purple, which has this is then the strength of this, some relative units. In the purple curve, that is the center of the G-band that has the greatest amplitude. In the long dash green, we have this extended G-band, which also is changing, not quite as large amplitude. And with a somewhat smaller amplitude, we have something just outside the G-band that is the same spectral region, but these are iron 1 lines in the vicinity. And they also change, but with even smaller amplitude. And one can ask, what is driving these changes? Well, one significant parameter seems to be the effective temperature of the model at each time. But the bottom line is this, that the spectrum, the atmosphere, the spectrum responds to changes in the atmosphere in specific ways, in specific radial velocities, in specific line strengths, in specific features. And these things can now start to be studied and calibrated, hopefully, against the extensive data sets of solar spectra recorded with these extreme precision exoplanetary spectrometers, where solar spectra have been taken with a cadence of roughly 5 minutes. So we have the solar radial velocity from the HARPS North. From a few months here, taken as an example, from 2016, 2017, the radial velocity here is becoming more negative. That is because we are on a declining phase of the solar activity cycle. We get less magnetically disturbed granulation, and therefore we get more free granulation and more blue shifted. And this is, as is known previously, is correlates with the Mount Wilson calcium K index. Calcium K emission, of course, also goes down. But that's not the only thing that changes. Other things change. The G-band changes. And the changes in the G-band are quite different from those in the calcium. And it's not just the G-band. Everything changes. The hydrogen H-alpha, the Balmer lines, H-beta change. Iron 1 lines in some particular group of iron 1 line changes. Some other group of iron 1 line changes. The iron 2 line change in a different pattern, and so on. And somewhere here, it should be, I think, possible to find a calibration or to understand what will be needed for a calibration to somehow say, enable the observation detection of also low mass Earth-like exoplanets. But there are things one can wish for. All things are not perfect. We need better laboratory data. For example, this is, if you take accurately measured solar spectral lines, in this case for the Kitt Peak FTS Fourier transform spectrometer from several years ago, and you compare the line shifts, in this case for titanium 1 lines, and you will see there is quite a spread over the bisectors around the average. Of course, part of the spread is due to line blends, but most of this is certainly due to finite accuracy or limited accuracy in laboratory wavelengths. The laboratory wavelengths seem to have accuracies of the order of maybe 50 meters a second for strong lines, from neutrals for resonance lines, and the accuracy gets less good for weaker lines and ionized lines. And one would like to have maybe 0.01 picometers, 0.1 milliangstroms, but that is not usually available. And the limitation seems to be not the limit in measuring precision, but the limitation seems to be the same type that we have for searching for low mass exoplanets. It's not a limiting precision of the instrument. It is a light source that is not stable enough. The laboratory light sources depend on the pressure, on the electric fields and whatnot. And I remember our late colleague Sven-Erik Johansson here in Lund, who was working with iron wavelengths and was concerned about some lack of systematic issues between iron 1 and iron 2. So they measured iron 1 and iron 2 from exactly the same lamp with the same spectrometer at the same time. But even then, they were realizing eventually that the tiny volume of emission of iron 2 came from some fraction of a millimeter closer to some electrode in the lamp than that for iron 1. And this illuminated the entrance aperture of the spectrometer slightly differently, causing systematic. So it's not an easy task, but it's an important task, because if one does not have the absolute line shifts, there are a number of things which become impossible to study. We also would like to have the radial velocities without spectroscopy to understand what are the true line shifts in stars. Is it only convective shifts, and what other shifts can we identify? In particular, the gravitational redshifts, which for the sun, so-like stars, are of the order of 600 meters a second, and they don't change very much along the main sequence. This is then the HR diagram. The gravitational redshift, because they're very small in giants, but the white dwarfs of the giants in this business, they of course have huge gravitational redshifts. Now, to determine radial velocities without spectroscopy is possible. It's not easy, but it is possible through astrometry, through second-order effects in astrometry. The simplest thing conceptually is just to measure the distance to the star 1 year and repeat it the next year. Simple in principle, but the parallax rate, even for the most advantageous star, is only 30-something microarc seconds per year. It will be marginally detectable with Gaia, but it will not be something to do stellar physics from. Another method is to study the change in proper motions. A proper motion is something like an arrow, a vector in the sky that is flying away from us or coming towards us. And that means that its angular extent will change from year to year. And this is becoming possible to measure. And this is from a recent study using Gaia and Hipparcos data, where this is the spectroscopic radial velocity in kilometers per second, and this is the astrometric radial velocity. And there is, of course, quite some scatter among the hundreds of stars, but for the better determined stars, things are becoming interestingly small. For Barnard's star, the nominal error is only 0.37 kilometers a second, which is then within the range of what convective shifts or gravitational shifts are. There is a third method, and that is to study the changing angular extent of something that is moving in space. And like a cluster of stars that's flying through space like a flock of birds, they are flying with the same vector. And that means that like a flock of birds, its angular extent will change with time. And you can tell what is the change with time that gives you the derivative of distance, how quickly does the distance change with time, and the absolute distance you can get from space-based parallaxes. The most advantageous cluster for this that's the Hydes. In this case, the noise limit is set by internal motions in the cluster, 0.3 kilometers a second or thereabouts. And these things can be improved, but probably not by a huge factor in a single manner. Finally, we want to have spectra without telluric contamination. We don't want superposed lines from the Earth's atmosphere. Of course, we have a heavy, in the infrared, we have a heavy, say, absorption from molecules of all sorts, not only water vapor, but also other molecules. There is much less in the visual, in the optical visual, but even so, it is significant. And here from some work by Bob Caruso, he has synthetic spectra where this is just some clean region somewhere in the optical. In the telluric, we have the blue curves here, both in the nominal strength and then 10 times amplified. Okay, this is the scale here. This is from 0 to unity for the full, and then amplified 10 times. And these sort of small absorption lines, they're all over. And yes, can you compensate? Yes, there are sophisticated programs that are compensating for telluric absorption, but they only do this to some certain limit. And of course, you would like to have something free from that. And it is sort of, well, one has to, it's sobering in a way to realize that never has there been any high resolution, high fidelity spectrum of either the sun or of any star ever been recorded from outside the Earth's atmosphere. Never. There have been some little touches. For example, this is one attempt from the Goddard high resolution spectrograph on Hubble, the spectrum of Sirius, that's the red curve here, going to the longest wavelength limit of the HRS on Hubble at 320 nanometers, 3100 angstrom somewhere, and then superposed here with as far to the shortest wavelength you possibly can go from the ground with some all-reflecting spectrographs. In this case, it is the Mount Wilson from Elizabeth Griffin. And the differences between these curves basically is the absorption of mainly of ozone. It just shows that you get something that looks like a spectrum, and of course it is a spectrum, but it is not the true spectrum. And further on in the visual, we have something that is contaminated in a more subtle and maybe more treacherous manner. So can we avoid this? Well, there have been proposals, there are proposals to fly high resolution spectrometer in space, the Earthfinder probe mission. Well, can it be done? Well, in principle, of course, yes. Will it be done? Well, not this year, but maybe one of these days also that will come. And somewhere here, I think I will stop and just summarize or to conclude that extreme precision radial-velocity spectrometers and the science that is coming with it, they enable also extreme precision stellar spectroscopy, but they not only enable it, they also require it, because in order to exploit the information about exoplanetary atmospheres during transit, there is a need also to explore extreme precision stellar spectroscopy. So thank you for listening.
Okay, thank you very much for a very nice talk. And now we have time for questions. Okay, there's a lot of rising. Rising hands. So if you want to ask something, please raise your hand, or you can use chat. Okay, Carlos.
One thing that occurs to me, and thanks a lot for a beautiful talk, is that in addition, I mean, you discussed the effects of granulation on radial velocities, and of course there are other effects that worry those that measure the search for planets, perhaps even more than granulation, which are effects coming from higher up in the atmosphere of the stars, right? The activity, magnetic fields, which are much harder to model. But I mean, people have been doing efforts also for a long time on modeling those higher layers. Do you think that the most recent generation of models of the chromospheres of the stars, for the sun, would be able to also help with the task of predicting the changes in the radial velocity?
Yes, a very, very good and very valid point. I did not show, but we have been looking also, for example, I show the G-band as an example. What does a G-band do in magnetically active granulation? I mean, it is possible to model not just say neutral, I mean non-magnetic granulation. You can also model it with various levels of magnetic fields. And also it is possible now to model quite realistically sunspots and sunspot, both umbra and penumbra. And in all of these cases, you can look at what is happening if you change something. And the hope is that it should be possible somehow to identify what is specific for each such component in a solar type star and how that will be modulated. And yes, absolutely, this is, it will not be a simple task to reach the exo-Earth specifications. One thing that has been discussed, and I know that Nuno Santos has been raising it. I don't know, I don't see him if he's in the audience, but is to have not only the sun as a star spectrometer sitting next to the planetary spectrometers, but having an instrument that picks out various pieces of the sun. I mean, an active granulation region, a sunspot region, etc. And data of such parts of the sun have never been studied with the sort of precision that we now have in exoplanetary spectrometers. For example, what is the typical fluctuations in this, and how the various spectral features will change? And I'm reasonably optimistic that this can be done because there is an enormous number of, to avoid the degeneracy, so to speak, is that we have very many spectral lines available. Some are magnetically sensitive, some are not. Okay, you may need extremely high signal-to-noise ratios and so on. We don't know this, but it should be possible to separate what comes from, say, star spots, what comes from stellar faculae, what comes from other chromospheric features. It won't be easy, but I think it's not clear, I mean, where the limits are. And in any case, it's clear that we can improve on the understanding towards smaller mass exoplanets. Whether we can reach an exo-Earth in the foreseeable future, I don't know, but that's the holy grail, or how to speak.
Thanks.
Okay, so please, Sandra.
Yeah, Bruce, actually, I use my wife's computer for this. I wonder if you could say a little bit about the trade-off between resolution and precision. For those of us who can't handle more than about 100,000 in resolution, but we can get higher or very high signal to noise. What part of this do you think was most appropriate for the high signal to noise versus that greater than 100,000 resolution?
Yes, of course. The purpose of these simulations with the hyper high resolution is not that we don't expect to have spectrometers with million resolution wideband anytime soon. So the purpose of these simulations is to identify, I mean, to see what effects exist at all, and then we degrade this. I mean, you don't show very much of this, degrade this to realistic resolutions. And then indeed one faces this, or is this question which you brought up, what's the trade-off? I mean, should you go for 200,000 and not as good signal to noise, or to go to 100,000 for the very high signal to noise? And that is different, I think, for each type of feature. For example, the G band, which I showed as an example, is a very broad feature, and that does not require higher spectral resolution to get resolved. If you want to follow changes in the G band, you need good signal to noise. If you want to look for changes in the width of maybe a magnetically sensitive single atomic line, then you need very high resolution, because otherwise that will be washed out. So that also one has to find some sort of optimum. What is the best? And what one can afford in terms of simply photon numbers and telescope time.
So is here somebody else who would like to ask something? If not, so I would like to ask you.
There is some.
There is, okay. Nice. Please, Professor Juliet.
Hi, can you hear me?
Mm-hmm.
Yes.
Sorry, my camera's not working very well. I really enjoyed your talk. It was fascinating. And the bit that I was really, that really was interesting for me, because I work in laboratory astrophysics and measuring these wavelengths of the atomic lines that you use. I was interested in your mention of the scatter and the problem that Sven-Erik raised many years ago. You mentioned with the iron 1 and the iron 2 and where the emission is within the light source. I would love to know if you have some data on that shows the scatter for this for different lines, maybe of a particular species that you've looked at, because we could look at this in the lab and see if there's some way of working around this problem.
Yes, the way one can see this observationally is if you take the solar spectral atlases, which are internally precise. I mean, there will be no difference between, ionized or neutral species because lines are intermingled. And then you find that if you plot the solar wavelengths shifted relative to laboratory ones, then there is this scatter that the strongest lines, the resonance lines, they have the least scatter, and then the scatter increases for the weaker lines and for lines of ionized species. And the desire, if one can wish, and I don't know, we and others have been using specifically also data from your group, is that if one can go from 1 milliangstrom to 0.1 milliangstrom in the accuracy, that would be fine. Because that means that in the visual, one goes from like 550 or 60 meters a second to 5 or 6 meters a second. And that is then a small enough quantity that can pinpoint, also quite subtle differences between different lines. But I realize that it's much easier to sit here and express a wish for this for very many spectral lines than that to be realized. But I certainly want to stress that laboratory work is very essential. And for example, we cannot, if it is predicted that the convective line shift is different in the short wavelength region than in the red. And this you can test if you can trust that there are no systematic errors in the laboratory wavelengths between red and between different wavelength regions, for example. How can one check this? I don't know exactly. We just wish to have the best data possible.
Well, we do try and check it because when we piece together the energy level system, it all has to match up. The UV lines, the visible, the infrared, everything has to connect together. So if there was a systematic shift between the lines and the infrared and the UV, it would show up. But our precision is down to about 1/10 of a milliangstrom, which we hope that we have our strong lines measured to. But I'd love to talk to you maybe at some stage in the next few weeks about the scatter that you see, and we could look at it just to see what it is and which species it's in, if it's in all of the spectra for the different ion group, for example, or just particular ones. Because historically, when we've looked at some data sets, sometimes the shifts disappeared when things were recalibrated. For example, in iron, there were some issues which were then resolved. So it would be really interesting just to find out a bit more. So thank you.
Okay.
I'll stop. I could talk for ages about this, but I'll stop now. Thank you. Bye-bye.
Okay, thank you. Any other question? Here's nothing in chat. And okay, if not, so thank you very much. Again, it was really very nice and very important talk. Really, I think I have to rewrite my lectures. But before we left, I would like to ask you something. We would like to give an opportunity to have talk also to young scientists and students. And there is the problem that because there were almost no conferences in last almost 2 years, so it's hard for us to know about somebody who would like to talk and for whom this talks will be helpful. So if you know about somebody, so please write me or Carlos or Katja, and contact. Thank you very much.
Thank you, Dainis, for a fantastic talk. It was very enlightening. Thank you.